So I'll try to wrap this up today. Last time, right, we saw a version of what I call the continuation theorem, which tells us, based on the exponential height of a germ, infinitely increasing germ, and the level, how far it extends on the Riemann surface, the logarithm. That's determined by the exponential height, and how it maps k-domains to what the images of k-domains are, which is determined by the level. Right? So, and then we also saw the consequence of that fragment principle that we looked at the beginning of the course, which actually allows us, when you put these two together, allows us to give upper bounds on the exponential heights of, say, compositional inverses of a given germ. So I want to take off there and make a definition. Okay, so a germ F in H, positive, say, or even in H, is simple if the EH is equal to the level. Right, so we saw the level is always less than or equal to the EH. That's just, that comes more or less out of the definition. And it's not always the same. Okay. So examples of simple germs, right, that's of course important for us, is all convergent transmonomials. A set of convergent transmonomials consists of only simple germs. Right, so here I'm identifying again, like the elements in H with their image in the Transseries as we constructed them. And also, actually, at the same time, the set of all purely infinite germs, okay, which are just the logs of the convergent transmonomials. Purely infinite. Again, the terminology, convergent transmonomials, purely infinite Transseries, right, refers to that identification between germs and their series that we made earlier in the course. Okay, all of these terms are simple. You can prove that. Yes, purely infinite convergent Transseries. Okay. Yeah, you can prove that by induction on H. It's not very hard to see. Okay, and of course, yeah, those are the ones that interest us. So for these kinds of germs, right, you get the following corollary. It's down again, the continuation theorem, and its converse or partial converse that I mentioned last time. So if you have two simple germs that are infinitely increasing, which means I can compose them. Okay. Then, all right, I can estimate the EH of F composed with G inverse. Okay, first of all, that's always more, at least the level. And for the level of the composition, right, that's the sum of the levels. So that's at least the level of F minus the level of G. Compositional inverse minus. Okay, but on the other hand here, right, from those propositions last time, you can say it's at most 0 or the level of f minus the level of g. Okay, so that's an application of those two propositions from last time. And so, for instance, what you get from this is, well, if you take simple terms of level 0, they form a compositional group. So, just as I don't think I'm using that. I am somewhere the proofs, but so set is 0 of simple terms of level 0 is a group on a composition. In that case, there's no room between the two inequalities. All other cases, I can't really say anything like that. Okay, but you see, so for us, I don't know if you remember. Maybe I should now draw that picture again, right? When we are trying to do our construction or generalize our construction of party field that we did for series log, x log, log, and so on. Right? So the schema that was the following: we start with a set of real numbers. We use the uniqueness principle the first time, right? And that gives us first QAT, right? Those monomials are just e to x. Generated by each. But if I want to end up with something at end that I'm going to call K F, where F is a tuple of say transmonomials, or more in my notation from last time, right, it's going to be a tuple of a purely infinite convergent transseries, because I take their exponential as the monomial. So we have Kf, and presumably the monomials will be e to the x composed with so this f here is a tuple. I don't want to put a bar on it because I need bars for other things. So it's just going to be this kind of thing where f is a tuple of terms. Right? I would like to end up in a QAA field whose corresponding transseries or series, series links are generated by these terms here. To do that, right, what I would do is I would be shifting on the right, first time not with log, but with fk composed with fk minus inverse. Yeah, right. And we would end up over here with a slowdown, corresponding slowdown, which I'm going to call host 0. This is what I call f1 prime. So here the monomials are going to e to the x composed with this fk minus 1 inverse. And then I will use the uniqueness principle again to add e to the x again as an additional generator. So we get something that I call f1. Here we get x and fk composed with fk minus 1. Okay, and so I will iterate this until at the last step, right, of new P. Over here, I would find F K, I believe. Numbering is correct. And the monomials would be F1 composed with F0 inverse up to Fk composed with F0 inverse. And that's always assuming that F0 is the biggest one. It's the smallest one. Right, so that's what I would like to do. So there's one more thing to compose on the right, which is F0. Then I would end. Right, that's the thing that we wanted. In order for this to work, we need to know that these guys here, well, not that one, but all the ones, the intermediate ones that I'm posing with on the right, have these holomorphic continuations on standard quadratic domains, and that they map any standard quadratic domain to any standard quadratic domain as a German. Infinity. Right, that was exactly the kind of question I had. And so, what can I say about these guys now? Right, this is exactly the kind of terms we are interested in when we start with something. Okay. So, that's a special case, one of interest for us, right? So, if F and G are both in U, so they're both these purely infinite convergent transseries. So that means these guys here will be monomers. So if they're in U, well, they're simple. So this corollary applies. Let's say, to get the inequalities right, F is the smaller one. I guess strictly smaller is good enough. Interested in it when they're the same. Okay, so if I have this, then that means what? The level of F is at most the level of G. This level is decreasing. It's increasing, sorry. On infinitely increasing terms. Okay. Oh, I see. Yeah, I should probably say infinitely increasing. Purely infinite could also go to minus infinity. I'm looking at the positive ones here. Okay. So level of F is less than or equal to the level of G. So what I get is that EH of which one? And when I do these guys, I always take the smaller one composed with inverse of the bigger one. In other words, that means here F composed with G inverse. Correct. That's the situation we have over there. And what is that going to be? It's going to be at most, well, 0 or the level of F minus the level of G, but that's 0. Okay. So by the continuation theorem, F composed with G inverse has an analytic continuation, sorry, holomorphic continuation to a -1 domain. That's much bigger than standard quadratic or anything like that. Much bigger. But it maps K domains to level of F minus level of G. Sorry, K minus that domains. Okay, yes. the angular level of this extension is level of F minus level of G. Okay, so that means it maps. Standard quadratic domains are zero domains in particular, right? So it maps standard quadratic domains at most into zero domains. And in particular, when you do if I make an additional assumption, if the level of F is actually less than the level of G, right? Well, then it will map zero domains to at most one domains. So one domains are domains whose boundary function already goes to zero. So in other words, as germs, right, it will map any zero domain into any zero domain, particularly into any standard quadratic domain. So then F bar, the polymorphic continuation, maps every zero domain into every zero domain. Not just standard quadratic domains into every standard quadratic domain, but every zero domain into every zero. Collapses things very at least one angular length.
Of G at all.
D?
The conclusion here does not mention G. It does not mention the.
Sorry, F. Sorry.
Oh.
This map, right? Map does this. So the ones, notice the ones that I'm plugging in here on the right. Right? So of course, that's for example the case, right, in our original construction when F was x, log x, log x, and so on, right? Then we have exactly this condition. The level of F minus level of G is -1. So under this assumption here, we can generalize already this construction. Right? As long as this tuple here, they're all elements of U. So in purely infinite convergent Transseries, such that the level of F1 is greater than so on. And K, we can construct this corresponding QA field. All right, it's a lot better, but that is not what I promised. Right? What about the things that are closer together? Okay, so what if I want to use the what if you want to use something like this? You want to use for F0 x, and then for F1 something like e to the square root of log. But that's smaller than x, isn't it? Yes, it's smaller than x. Okay, those are two functions in U. Sure. Okay. They both have level 0. So that's certainly not going to be true. But I still want to be able to use these. When you look at the monomials, but when you compose this on the left by x, you get perfectly independent set of monomials. Everything's fine in the scale. So what about this? We still do it. This kind of stuff. So I just want to mention a little bit that in fact this is possible. So let's see. Yeah, I'll just state the theorem first. So the thing is, continuation theorem, as I stated it, I was unable to prove it by induction. I was unable to carry that statement through the induction to prove it for all terms. You needed additional kind of technical sounding assumptions, like things. Some of these are fairly straightforward, like the idea that if I have a real domain, I have a real domain, and I have one of these extensions of a germ to a definable real domain, right? It maps the reals to the reals, which means what's above here has to be mapped either above or below. But you cannot map something above here to above and something else above here to below, because this guy here separates these real domains. And so which terms do what? Turns out that the terms that are infinitely increasing, they map things up here to up here. So they preserve the sign of the argument. Whereas maps going to zero, invert the sign of the argument. So it's kind of an obvious statement that you add, and it's very important, as it turns out. So that has to be added to the statement of the continuation theorem in order to be able to carry it through the induction. There is a couple of other technical things like that one has to add, but that's an important one. Right? And the thing is, after you have added that to your continuation theorem and you're able to carry it out, we can actually get a more precise description of the tuple for which this works that includes, for example, this pair. Okay, so I call that the admissibility theorem. So that now describes what tuples F, like over there, we can actually make this work. Okay, so if you have a tuple that are all represent different Archimedean classes, okay, and that kind of makes sense because you don't really want to. Right? What does it mean to represent different Archimedean classes? It means that these monomials here, right, represent different probability classes. So that is usually what we expect to be necessary or to make sense of things. Okay, so let's say they're not just ordered by the usual ordering, but by the domination ordering. Right? So let them be simple again. Terms in I, so infinitely increasing. Okay, so I'm going to write F for the tuple. So generally, right, when I have a tuple like this with these indices, when I write the corresponding letter without the index, I mean the whole tuple. I don't want to put bars on because I use bars on the board here for these homomorphic continuations. Or F1, okay, why not F0 like I have it over there? Doesn't matter, of course. Okay. So then we can say the following. So this follows from the full continuation theorem. Right? So not from the statement that we discussed on Monday. It's not good enough for that. But things like this preserving sign or even inverting sign on the argument is also important. So then we get actually exactly the things we need to carry out this construction. So we need to know, right, for any pair of these FIs, so 1 less than or equal to I less than J less than or equal to K, sorry. And every standard power domain. So this is the one thing too that I have to be careful about here, right? For the original construction with logs, we just needed to look at standard quadratic domains. Turns out that it's not enough for the general germs. So that's why I introduced the standard power domains. Remember, it's standard quadratic domains, you use the square root, right, in the definition of the domain. you replace the square root, which is power 1/2. And any epsilon between 0 and 1, everything goes through. Okay? But I need to use those here. So for every standard power domain B, there exists a standard power domain U and the holomorphic continuation, which I'm going to call Hij, Fij, I guess, of, let's see, I is less than J, which means Fi is bigger than Fj. So I should look at Fj composed with Fi inverse. Right? Yes. So this is the holomorphic continuation of that one, which we obtain like in this special case. Okay. Such that. But now I'm just looking what happens at standard power domains. And I don't need more for that construction. Such that Fij maps U into V. Right? That's what I need so that I can plug them in on the right thing. And two, yes. Right. At every stage of the construction, like what are the monomials? It's these kinds of things here. They form a scale on standard power domain. I equals 0 up to k. The monomials. E to the x composed with the tuple. Let's see, we have as stage. Okay, so I guess we have I plus 1 composed from F inverse up to Fk. Those are the ones used at each stage. They form a scale. On standard power. Let's say the admissibility theorem says exactly that simple terms that represent, right, that are ordered and whose all represent different Archimedean classes. This construction is. Okay, so at the moment I don't want to prove this. Let me point out how we're going to time for that. And we can leave that for. Is there still another question? Oh, we had one yesterday. Yeah. So anyway, we'll see, but we can figure this out. All right. So what this means is when we get any such this construction goes through for any of these two. So for any tuple F0 tau is greater than so on K I there is a QA algebra field I'm going to call it not F but K. Where the monomials are e to the x composed with F, the last stage. And then corresponding map series, right? And so these are series or transseries, convergent trans monomial, guys. Yeah, there's a QA field like this, And along the way, you can show that if you have another tuple, sorry, this is in I, any simple type, any simple, yes. Any G are also simple. And well, F0 up to Fk are a subset of the generators G0 up to GL. Right? And the corresponding algebra for G extends to 1. Like we probably expect. Kg EXG GD extends. Dx F and T. Okay. So we get a directed system of these algebras, and we can take the derivative. That's the big thing.
The initial segment of gratification. Initial segment of G0.
Not the initial segment, just the subflexion of the generator.
Just
Doesn't matter where they are in the. You can add things in the middle as long as it doesn't make a difference. But that's where you have to work a little to show that it doesn't make a difference. So, good catch, right? In that sense. Yeah, so that means right, K. Okay, what's the direct limit of all these transmonomials here? It's just going to be L. Instead of all conversion transmonomials. So K L T direct limit of the system. Direct limit. So right, so in other words, right, the collection of all these QA fields is partially ordered by the order of these tuples. Instead of these finite subset. Okay. Of all these F. Okay, so that's one big QA field. And all the image, right? The image of this and the T is a is inside the Transseries, but it's only Transseries whose transmonomials are all convergent. But they are generally divergent by the way you're constructed. Dirac series are in here. Almost regular terms are all in here. So, in particular, right? K, this guy here, extends. All right, the one that we saw for H and X, where we had L, and we had what do you call phi? And we had the map phi from now Dave and Angus's paper. So this QA field extends that one. It also extends the one we constructed at the beginning. Okay, we also use the letter T there. So, like L was the set of just all log numbers. Okay, so it extends both of these. Remember, this one did not contain that, or vice versa. Oh yeah, and there's other things. Yeah. So the nastiest part of all of it is that K is actually Hardy stuff. Okay, So that is not true for the intermediate steps here. At least I don't know. I don't think it's true. K is a Hardy field and T preserves. Differentiation.
And that's this thing into the differential field of Transseries.
Yes, exactly. T preserves differentiation, right?
Right.
It ends up in the set of all Transseries whose transmonomials are convergent.
Is this also close to the composition, this K?
No. It's not. So I want to show you that, but it's actually easy to see exactly because it only allows convergent transmonomials when you compose on the left, but it contains divergent Transseries, right? So when you exponentiate something like that, you are not back in your feet. It's impossible. You will pick up divergent transmonomials. So they are not in there. Okay, let me just give you. I think I have an example of chiron example, right? Oh no. Yeah, somewhere I do have one. Ah, right. Yes. There you go. So this K is now closed. X, say. Okay, so what is that? Right. So we already know that we contain these almost regular germs. We know there are almost regular germs with Dirac series or divergent. Okay, so take one of those. So take F in K with a divergent Dirac series. Right? You know that you're there. So then what do you do with this? So the Dirac series, let's call it T of F, right? According to that notation, which is some, say, let's even, right, it can even be a Dirac series where there are no logs. So from, a non-resonant hyperbolic polycycle or something. Okay? So some AR e to the minus Rx. Okay, so we know that these things exist. Okay, so then F multiplied by E2, e to the x, okay, that's still going to be in K. But e to the x is in K. Right? So that's still in K. And its series, of course, is just T of F times E2. Okay, so what's T of F times E2 as a series? This is purely infinite. Okay, and it's a divergent series. It's a true series, not just a polynomial. Okay, it's divergent. So, which means x of this series is a divergent transmonomial. And so it's not in the image of T. Okay. So yeah, right. It's certainly not closed on the exponentiation. So there's a first interesting question that I'm still not entirely sure of, but something that so hard to figure out. So what this theorem over there suggests, right, is that T of K is what might be what Van der Hoeven calls a transserial Hardy field. Is T of K a transserial Hardy field? So, and most of the definition of transserial Hardy field sounds exactly like it's the image of a QAA field that's closed under differentiation. But there is a couple of extra conditions on it, which has something to do with logarithms, I think. I don't think it's quite that it has to be closed on the logarithm. But you see, closed on the logarithm, that's not a problem here. So that thing, I believe, is closed on the logarithm. You don't pick up any divergent transmonomials that way. That goes the other way. So it's really right the question of does T of K, is that actually a transserial Hardy field? If you know that it is, you can apply his theorem, which says that you can always close a transserial Hardy field under X and under integration and get another transserial Hardy field. And then, of course, the preimage of that would be another QAA field closed under differentiation. Right? So there might be a canonical way to extend this further into something that's at least you will close. So yeah, that's something I could look at. It might be easy, it might not be. But yes.
Okay, well, let me see. It's
I don't exactly remember the law condition that's involved.
yeah,
It didn't quite sound like
is the image is TK let's say grid based? That means in every.
No, that it is not.
Oh, it's not.
So, but in his paper, he says, okay, I work with grid based, but you can do everything without grid based too.
Right. Yeah,
So no, this is not grid based. Okay, so that's true. Not grid based because of the way I allowed everything from the start, right?
I see. Yeah.
But if we are to believe yours, then that shouldn't really be a problem.
Well.
Okay.
Okay. Right.
So see, there is some problems to be checked here, but I still think it would be an interesting question, right? Because I would like to close it under X. I can't do it this way because exactly of this counterexample, you can't expect to close under X using this construction.
There are more general. I mean, once you have an embedding of a Hardy field into T, into the field transseries, you can always extend it to an embedding of the Liouville closure of that Hardy field into T. I mean, such theorems exist.
Okay.
Uniquely, even.
Uniquely. Okay.
Completely.
Would that embed, and I guess that embedding would still represent asymptotic expansion. Like.
Yeah. Absolutely. Yeah. So one doesn't need this harder theorem about.
Okay. Well, yeah.
I think.
Great. I would like to know.
Of course, it's still a good question, but
yes.
As far as embedding into the Liouville closure of K into Transseries, that is not a problem.
But is this your condition?
That kind of thing.
That I'm not sure. Well, I suspect it does, but I'm not sure now. But is that needed?
Well, I would like it.
Yeah.
Right.
Sure.
It's here. It's true. Right. For K, it's true. The T preserves. Right. The image is truncation closed, and T preserves truncation.
Yeah.
That's how we. Right. I think one of the conditions on this definition has something to do with that.
Right.
But again, that is true for my K. So
I think it's probably true also in. Anyway, I can think about it. Of course, the other thing is this contained in the Hardy field of an o-minimal expansion?
Well, that I don't know yet.
That is
the big question, of course. Yeah. Does this generate nominal structure? So does K generate minimal expansion of the real field. And remember that was actually the motivation in the first place to look at this, right? Of R-bar. Yeah, that's the big question. Again, that is something that I think we'll be working on a bit. There are some things that we are trying to do. Lots of it is still very speculative, but it's possible. I mean, the conjecture is that yes, it is. It just has to be. That's how.
Right, but for this K, what is it? This earlier version of it.
That's that F.
Yes, there it is known to be contained in the o-minimal.
No, it's not. No,
not even that one.
No, because it contains the almost regular germs, and we don't know if they live in the regular structure. Yeah. No. So, yeah, I mean, one of the reasons for this extension was that having this K at the start would give us a more flexible way to define several variable functions that we need in order to prove o-minimality, right? So in several variables, right, what are the generalizations of these Transseries? It's kind of seems a little limited, but it might not be. No. But if you're allowed to use all these monomials here in one variable, then maybe you can use all definable germs in RNA as monomials, potentially several variables. That's kind of the whole. So somehow having this guy here suggests we might have one way to try and prove this. That's kind of how we looked at this first. So there's now several ideas floating around and how we could use that to generate several variable functions for each o-minimality. None of which seem easy to do. Yeah, I guess. Yeah, so I like I said, I'm not proving the admissibility theorem, but it relies on these extra technical, so-called technical notions. You just need to prove the continuations. Just happen to be the right thing to actually extend this construction, all the proofs that I want. Okay. Thank you for listening. Okay.